And thank you for joining us today. It's a very good evening as of Wednesday yesterday to Professor Stephen Hillis, who's joining us today from the Departments of Radiology and Biostatistics at the University of Iowa. And we're so grateful for his time and expertise. Steve typically has written the most modest and briefest bio, but Stephen is a research professor in the Departments of Radiology and Biostatistics at the University of Iowa, and he earned his PhD in statistics in 1987 and his FMA in music, and probably tell us a little bit more about that at the end, Steve, in 1978, and both of those were from the University of Iowa. He's authored over 100 peer-reviewed journal articles and 4 book chapters. And since 1998, his research has been focused on the methodology of multi-reader diagnostic radiological imaging studies. It's been a pleasure to welcome Steve to Australia a couple of times as a visiting professor. We always enjoy catching up with him overseas, particularly in the US, where he presents at many of the world's top imaging conferences. And I'm delighted he's accepted the invitation to talk today on the methodology for analysis of radiologic diagnostic imaging studies. And Steve, it's over to you.
Thanks, Sarah, very much. I'm just fooling around here looking at the people that are there. Is there a way to get, so I can enlarge, I can see everybody's thing on a grid? I haven't, let me just see here.
You can try and alter if you go to the little view icon at the top right-hand side of your screen, you can try and have a...
Oh, yeah, yes, that's it.
Yeah.
That's it, yes. I've got it on the other computer, so I can.
Yeah.
Yeah. It looks like in the beginning I just had 6 people on, and now I can see there's others.
Yeah. So at the moment we have, well, taking away yourself, we have 17 people online, and really we're a mixture of across a few universities in Australia. So the University of Sydney, Monash University, University of Melbourne, plus some wonderful colleagues from the Australian synchrotron, also in Melbourne, and others.
Okay. Well, thanks very much for inviting me, Sarah. I enjoyed my visit to Sydney, some years ago. I can't even remember how many it is now. I think it was maybe 6 years or so. But it was really very nice to be there for, I think it was 3 weeks, and to meet everybody. So anyway, tonight, this is my talk, Wachowski-Rocket Hillis methodology for analysis of radiologic diagnostic imaging studies. Actually, I don't think that's quite I think I forgot to change the title here, maybe. It's from another talk, but it's about the same thing. So I'm just going to kind of give a quick view of the Wachowski-Rocket method. So let's get started. This is the outline of the talk, introduction, the Wachowski-Rocket method, and then OR analysis using R program, the R program MRMC AOV, then about making conclusions from OR analyses and the readers nested in test studies. And the last one, the readers nested in test analysis, is what I talked about when I was at RSNA this year. And that's when Sarah mentioned she had another study like the one I was talking about. Okay, now if you can't hear me, just let me know if I need to speak louder or more distinctly or not so fast. Okay, let's see here. So overview. So I'm going to start out with kind of a basic overview. I'm anticipating that most of you aren't statisticians and just have a very, very basic knowledge of statistics. And so I'm going to skip a lot of the formulas in here. Okay, so in radiology, medical decisions are made on a radiologist's interpretation of an image or a set of images acquired using an imaging modality such as MRI or CT or X-ray. And for example, mammography, a radiologist looks at an X-ray image of breast tissue and gives an opinion. Now, the important thing here is that there is variability between both radiologists and cases. And so it's that one aspect that led to the development of the OR method, because we need to account for conclusions to be strong if we want them to apply to both populations. So we want to compare two or more imaging modalities, typically, for instance, our digital mammograms, non-inferior to film mammograms, etc. So typically we compare reader performance outcomes under two or more imaging modalities. Typically the reader performance outcome will be a measure of how well the reader can discriminate between diseased and normal cases. And the reader performance measures are typically functions of the receiver operating characteristic or ROC curves estimating for each reader. An often used reader performance measure is the area under the ROC curve, or the AUC, which estimates the probability that a reader will correctly discriminate between a randomly chosen diseased and normal case. So that makes it a very nice measure because it has a very nice intuitive interpretation that most people can understand. And this is an example of a typical radiologic multi-reader, multicase, or MRMC diagnostic study. I've been using this study for a while because somebody gave it to me a long time ago and made it available. Carolyn Van Dyke study from 1993. There were two modalities, single spin echo MRI and cinematic presentation of MRI or sign. There were 5 readers, 114 cases for patients, 1 image per case. There were 45 diseased patients, 69 normal patients. The readers were asked to rate each image using a 5-point ordinal likelihood scale for presence of aortic dissection, which was our disease. Readers read images using both modalities. This is a typical MRMC study design, and it's referred to as a test by reader by case factorial design. And the word test can be a modality, a treatment, reading condition, etc. More generally, we want to compare tests with respect to reader performance, such as a measure such as the AUC. And in our example here, the AUC estimates, these are based on a binormal ROC curve estimate. And as you can see, spin seems to be doing a little better than sign. Okay, so these are our main outcomes, our 10 outcomes, 5 readers, and they're reading under each modality. And these results suggest that reader performance may be better for spin, echo. So typical MRMC factorial study characteristics, the number of readers is usually quite small, typically 5-10, because usually there's only a few radiologists available for most studies. Number of cases is usually on the lower side of moderate, usually 25 to 100, each of diseased and non-diseased. And again, why expensive? It's expensive and time-consuming to verify the truth state of cases for being read. And of course, readers have limited time. We want conclusions that generalize to both the reader and case population. So this is, again, the important point why we have the Obuchowski-Roquette method, so we can get these kinds of strong conclusions. And the only way of saying that is we want to treat both readers and cases as random. So the comparison of interest is simple. We compare the reader performance for the 2 tests. Now, I'm going to talk about the conventional ANOVA model analysis that treats cases as fixed. If we are okay with limiting our conclusions to the study cases, and hence would be, as we say in statistics, treating cases as fixed, then we can use a conventional ANOVA model with IID errors, independent and identically distributed errors. The errors will be independent because there is no correlation resulting from reading the same cases, since the cases are treated as fixed. Okay. And so this is our standard ANOVA model that you learn about in your beginning ANOVA class or regression class. And in radiology, the test factor is typically an imaging modality. So that's again, these modality and test interchangeably. Now I'm going to skip most of this notation here. But this is the conventional ANOVA model with fixed cases. Data had IJs, the AUC. mu is the fixed test effect, tau I is mu is the intercept term, tau I is a fixed test effect, Rj is a random reader effect, tau Rij is a random reader by test interaction effect, and this is the error term. And all random effects are, including the error terms, are assumed to be mutually independent and have normal distributions with zero means in these variances. Okay, so you don't have to understand all that. This is I'm going to really skip this page. This is the F statistic. This is the mean square for test, the mean square for the interaction. And this is, how we test null hypothesis of equal AUCs. Okay, so that's again, the statistical part, which for this talk, you don't have to understand. And you would see this in your basic ANOVA class. And there are two tests, this is basically the same as a paired t-test, okay? And then the statistic can be written in this form as the difference of the AUC, the average of the test average, the AUCs, and divided by their estimated variance. And then we can get a 95% confidence interval for the difference of the AUC means. Okay. Now, what's wrong with that approach? Well, the problem with this approach is conclusions apply to the population of readers restricted to reading only the study cases. In other words, conclusions do not apply to the population of cases. So in the United States, if you put in a request, if you do a study on some new imaging device, the FDA here, Federal Food and Drug Administration, will almost invariably require that your results apply to both the populations of cases and readers. So the Obachowski-Roquette method was developed just for that purpose. Now, you may have studied random effects models in your statistics classes before. And the reason we can't use those standard methods is because in the field of radiology, the AUC is a different kind of animal. It's a different kind of summary measure, and it doesn't fit into those kinds of models. So that's why Obachowski-Roquette developed this method back in the mid-90s. So first paper, 1995. And again, reader and case are treated as random factors. It's the same as conventional ANOVA model, except that to account for case variability, the error terms are allowed to be correlated. And that's all it is. Conceptually, all it is we're taking the model that we would normally use if the errors were independent, and we account for the correlation. So the ORR model is the same as conventional model, except for two aspects. Since the same cases are read by each reader using each test, the error terms are assumed to be correlated, and the denominator degrees of freedom are computed then differently. Now, there are three possible covariances for the errors. And this is important to remember, at least conceptually. Covariance 1, it describes the covariance between a pair of errors corresponding to two different tests but the same reader. Covariance 2 is for the same test but different readers. And covariance 3 is different tests and different readers. Okay, so there are these three covariances in the model. And they assume covariance 1 is larger than covariance 3 and covariance 2 is larger than covariance 3. And I've proved why this last one has to be the case. That's an important constraint on the model. It should make sense that the correlation, if you're in the same test with different readers, should be larger, if anything, than if you're looking at different tests and different readers. So covariance 1, 2, and 3 are typically estimated using the jackknife DeLong's method or the unbiased method, which is due to Bamber in 1975. and that's only for the empirical AUC. Okay, so here's the OR ANOVA model. We're testing the null hypothesis of unequal tests. So here's the F statistic, and then here's this, what we call the non-negative correction term. So again, these are mean squares, mean square test, mean square interaction, test and reader. Those are the same as the conventional mean squares, conventional ANOVA mean squares. These are the hats indicate the estimates for covariance 2 and 3. This delta is the maximum of NR, that's number of readers, times this difference of covariance 2 minus covariance 3, or 0. So this then can't be negative because it's a maximum of 0 and this term here. So this is a non-negative correction term that accounts for correlation in the errors due to readers reading the same cases. So the only difference, this is an important point, the only difference between the OR and the conventional fixed cases, ANOVA F statistics is the correction term. That's the only difference. Otherwise, if you take this thing out, you just get the conventional model. And delta imposes this constraint again. The covariance 3 minus covariance 3 has to be non-negative. And by the way, if you have any questions, you can just send me a note. Or, speak up. Okay, I like questions. All right. So again, we can get the F statistic, and then there's the denominator degrees of freedom that has to be different from the conventional model, and this is what we call DDFH, and the H is because I thought this one up, and the reviewer made me put H in to indicate that it was a Hillis. In creation or whatever, I don't know. Okay, so that's it. Here's a p-value. And I mentioned Obachowski and Roquette. You see a different degrees of freedom, but this was too conservative, and then I proposed this in 2007. And this is just a Satterthwaite approximation that treats this quantity as a true value, plus no variability, by giving it an infinite degrees of freedom, and that's reasonable because covariance estimates are typically based on a fairly large number of cases. Okay. Now, there are two tests, and we can get, of course, a statistic looks like this. And we can get a confidence interval. And again, the formulas are the same as for the conventional ANOVA with fixed cases, except for the correction term and degrees of freedom. Okay, any questions so far? All right.
No, I think I asked people to pop their questions in the chat, Steve, or we'll ask you at the end if that's okay.
Sure, that's fine. It's all, you know what? I see the chat has 5 questions in it. Okay, good. I didn't see it up there. I haven't been on Zoom for a while giving a lecture. I gave a class a couple of years ago. Okay. Well, there's one from Sarah saying, everyone's welcome. Okay.
Yeah. Yep.
Okay.
No, we don't have, there are no questions. There are no questions yet. That's just people introducing themselves. So.
Okay.
Sorry, Steve, can I ask with your assumption of covariance 2 being larger than the third one?
Yes.
Is it possible to test it?
To test if it's larger? So that's a good question. So in reality, sometimes the estimate will be smaller, and that's why we constrain it. So recently, so in a recent paper I did last year, the year before, I proved that covariance 2 cannot be less than covariance 3. Okay.
Mm-hmm.
I mean, I think intuitively it makes sense, but under very reasonable assumptions, it cannot be true. Mm-hmm. That's a good question. It turned out they had assumed actually the covariance 1 had to be bigger than covariance 3, but I see no reason why that has to be the case.
Okay, thank you.
But that's a point that, as you'll see, that's a constraint that will come up again. Okay, anything else? Thanks for the question. Makes it more interesting for me when you ask me questions. Okay, so here's again the Carolyn Van Dyke study. I read through that again before, so I won't read through it again. Oops. See, oops. Right. Okay, we call that study. Okay, now we're going to go on and analyze that data using the R program that we've created. This was created as part of my recent grant, MRMC AOV. The AOV stands for Analysis of Variance. MRMC stands for Multireader, Multicase Studies. Is R something that people there use? Anybody want to? Sarah, what do you think?
Yeah, so the university, I don't personally use it. The university does support the use of R though. But I'm not sure if anyone on the call wants to say that they use R.
What kind of software do you use? I mean, you don't have to know R to follow me, but I'm just curious.
I have used R, but I know if a few other people on the call have used that as well.
So,
but they also use Python and
Python. Huh?
Yeah.
Anything else? You don't use SAS there, do you?
Stata.
SAS, SAS. Then the state had these data. Okay.
Yeah,
okay.
the uni, you can use that through the uni, but I personally don't use it.
Yeah. Well, so R is a free language. Yeah, it's available for free. And as you'll see, we've got a program that it's pretty easy to use, but at the same time, it does. I didn't learn R until the last 2 or 3 years myself. To use. I used to use SAS, and nobody uses SAS. I found out for the most part because it's very expensive. So anyway, the purpose of the talk is you don't have to understand R to understand the talk. Okay, I was just curious. So on the following slides, I showed the OR analysis of the Van Dyke data using the newly created R package. And we created this as part of my grant. And the main programmer for the software is Professor Brian Smith, and he's in the Department of Biostatistics. And he is an excellent programmer. I mean, he is just super. And it was really great to work with him for the last 5 years. The Van Dyke data set is included in that package. Okay. So here again is the Van Dyke data as it is in the package. Reader, treatment, case, truth, and rating. And then this is how we, oops, sorry, I keep hitting the wrong thing there. How we analyze it. The first statement in blue is what I typed into R, and then it just kind of repeats that here, the call. So the idea here is it's going to be the empirical AUC, and these are the truth and rating variables. Test variable is named treatment, and the reader case, and the data set name. And if you have different variable names, then I would specify them here like they show here. Okay. And then they show you, this is the output of the AUCs here. So 114 observations. These are the AUCs. These are the treatments, and these are the readers. This is the ANOVA table that I showed you that, and these down here, the Obuchowski-Roquette error variance and covariance estimates. And I know it's a little bit blurry. That's because I've pasted these in directly from the output. And the important thing here I want you to notice is here are the covariances, covariance 1, 2, and 3. And you see you have the right ordering. Covariance 1 is larger than 2 and larger than 3. And then here are the correlations. And these correlations are just these things divided by the error variance up here. Okay. So like I say here, correlation 1 is 0.3046. 0.00346 divided by the error variance, 0.008. Okay. And so these are nice because they go from 0 to 1, and you can they're easy to interpret between studies. Okay, so Again, this is the output, multi-reader, multi-case analysis of variance, data Van Dyke. We have random readers and random cases. Covariance method, we're using a jackknife for the covariance method. The design is factorial. Okay, and again, the covariances. And here are the reader and the interaction variance components. Okay, so here's more output, and I've indicated to you what the important parts of it are. These are the global tests of equal treatment empirical IECs, and we have p-value just slightly non-significant 0.051. And then here are the 95% confidence intervals and tests. So we're comparing, this is the confidence interval for sign minus spin, the sign AUC minus the spin AUC. So the estimate of that difference is 0.043. And this is the estimate of the confidence interval. And then again, the p-value here, since there's only 2 treatments, is the same as the global. And then here we have the empirical ACs, confidence intervals for the individual tests based only on data for the specified treatment. And now I say, recall, this is our F statistic, and this is here, this is the correction factor. Okay, and then that's what it looks like here. And then number of readers 5 times the difference of these 2 covariances, covariance 2 and covariance 3. Then we get the p-value. And I just say the last part of the output here, this is based upon the single test OR model, which I'm not going to talk about today. Okay. Now, and then here's a plot of the ROC curves it gives you. And as you can see, sign looks like it's the better one. I'm just looking at those curves because it's generally higher. And now you might say, well, I mentioned there are 3 different covariance methods we can use. Which one should we use? Well, generally, here's a jackknife. That's what we actually, what did I use? Well, I did something a little naughty there. I said I was using a jackknife before. Actually, I used a DeLong. That's a 0.0512. Here's the jackknife, 0.0527. And here's the unbiased. As you can see, there's hardly any difference. So it doesn't matter too much which one you use. And now, making conclusions. You've got the output. What can you say? And this is I think, a very important part to understand. So there was not a significant difference between the sign and spin echo reader average TUC estimates. However, simply stating that there was not a significant difference is typically not informative and can be very misleading. Okay, so I advise you never to just stop there, because that doesn't really mean very much. So when there's not a significant difference, the 95% confidence interval for the difference should be given. At least that's what I recommend, since that will indicate the range of the true difference that is commensurate with the data. For example, I could say the 95% confidence interval for the sign minus spin AUC difference was this. So thus we have 95% confidence that the sign AUC is between 0.0004 less and 0.088 more than the spin AUC average across both the reader and case population. I'm looking at that and thinking, did I get that wrong? Let's go back for a moment. So, actually, so sign looks better, doesn't it? Spin.
On your original ANOVA, Steve, it was actually the spin that was higher, I think.
Yeah, I'm looking at this and thinking, I think I good, Patrick, you caught it. I just made these slides in the last couple of days, so you remember that well. Okay. You know what? I think what happened was, okay, I apologize for that. What happened in the last day or so, before the tests were indicated by just numbers 1 and 2. So I decided, to make it clearer for the talk, I would change them to their names, and I think I got the names backwards. Okay, so I apologize for that. Yeah, so it should have been the other way. Spin was better than sign, which doesn't really make sense, but maybe that's why the paper never got published. Okay, so you get the idea. If you report the confidence interval, then and you can understand, how close do we think these two modality AUCs are to each other, and that gives a person, an understanding. And then typically, I think I said later on. Typically, we're not interested in just do we reject or accept the null hypothesis of equal AUCs. Typically, I think you're more interested in, if anything, proving non-inferiority, especially when you have a new method. And regardless, what you just do by looking at the confidence interval. So the confidence interval is very easy for everyone to understand. They can see where that difference is, based upon the data, and it just makes a lot more sense. So, again, when you hear someone say, "Oh, we didn't find any difference," that doesn't mean there wasn't any difference. It just means it wasn't. Statistically, we couldn't find anything. So it doesn't, it doesn't really tell you anything at all, in my view. Okay, depending on the research question, you would then make practical conclusions given this confidence interval. And then note again that our conclusion generalizes to both the reader and case populations. Okay, so I'm going to pursue this a little more. I'll give you another example, making conclusions from confidence intervals. Here's some excerpts below from a recent paper by Lori Fajardo in 2022 in Radiology, pilot study to assess the performance of phase-sensitive breast tomosynthesis. And this was well, I'll read the abstract. In this pilot study for an inline phase-sensitive breast tomosynthesis system, or PBT, the true diagnostic performance of PBT was within 0.08 of the true diagnostic performance of standard digital breast tomosynthesis, with PBT having a 24% mean radiation dose reduction. So again, this part here is based upon the confidence interval that we got. Actually, as a confidence interval, I'll show you a little more about it. So this again from the article here. It says average across the 9 meters, the mean AUC values were 0.74 for both PBT and DBT. So they came out with the same AUC estimates. So treating both cases and readers and cases as random, the 95% confidence interval with the DBT minus PBT difference was calculated as by this confidence interval, negative 0.08 to 0.08. So that's where we see, oh, they're basically within 0.08 of each other. Okay, that's a maximum difference. So that gives a reader, an idea of how well this new modality works. And this was an initial study. They were just trying it out. So I mean, 0.08 isn't great, but for a new study, not bad. And the fact that the estimates were the same looks pretty good. And it got accepted into Radiology. And in conclusion, they wrote, we estimated the diagnostic performance of phase-sensitive breast tomosynthesis as measured with the area under the receiver operating characteristic curve was within 0.08 of that of digital breast tomosynthesis at a mean radiation dose of 24%. This supports the feasibility of applying PBT clinically as a breast imaging modality with the benefit of reduced radiation. However, system modifications, and I emphasize here now, larger studies are required to establish the non-inferiority of PBT. Okay, so this is a paper, I was a co-author on this paper, and we had a lot of arguing, going back and forth between me and the other researchers and the editors, because some of the other researchers wanted to say, hey, we're doing just as well as DBT with PBT. Okay. And then the editors of the journal were saying, no, no. And at first I was going, okay, you want to say that, I won't make too much of a fuss about it, which was not good. Ethically, it was not correct of me to do that. I should have been tougher on them. But the editors of the journal were tough. They said, no, no, that's not, you can't say that. Just because the estimates came out the same and it was a non-significant difference doesn't mean that they're equal at all. Okay. So we went back and forth, and these are the statements we came up with in the end. Okay, my perspective is that for the majority of diagnostic studies, we are more interested in comparing two modalities with a confidence interval than simply concluding a significant difference or no significant difference. Even when we are interested in testing for non-equivalence, I recommend always also giving a confidence interval in addition to the p-value. Okay. So I have a question here. Oh, R, Python, and MATLAB. Yes, thank you. Oops. Okay, let's talk about fixed readers and fixed cases analyses. And I'll go through this pretty quickly. Conclusions generalize that both the populations of readers and cases are the strongest, so these result from the usual OR analyses. However, the OR model can be easily adapted to give conclusions to treat either readers or cases as fixed, and hence to not generalize to their respective populations. And why would we want to do one of these analyses? Well, sometimes we may only be interested in inferences about the reader population when reading a particular data set, such as one that has been artificially created by adding lesions to the images. This is often done in SOS or satisfaction of search studies. Also, if the result is not significant using the general OR method, then it can be informative to run the fixed cases or fixed readers analyses for comparisons, since they usually will have more power. So even if you don't get a significant result, you're curious, well, maybe I would have more power if I, the test that fix one or the other, and that would be encouraging to you. And I think you might argue, Patrick, that with your data set, with the breast data set, maybe that's the only data set you're interested in too, because it's it's not exact. I don't know. It's not it's not been selected from a random population. I mean, maybe it has, but we won't get off on that tonight. But I'm just kind of thinking aloud here. Okay. Now I'm going to describe fixed readers and fixed cases versions of the OR method. So the OR model becomes a conventional ANOVA model if the error terms are assumed to be uncorrelated, that is, covariance 1, 2, and covariance 3 are 0, and hence treats cases as fixed. So we can do this easily in the software. We just put in here the cases as fixed. That's all we have to do. And then we run the software and we get the answer. And I'm not going to read all that to you. There's no, as it says, overcharge for variance component covariance estimates are not applicable because cases are fixed. Here's the summary, and the p-value here comes out to be 0.04. Okay, 0.42. And remember what it was before, it was 0.052. And that's why I note on this page that conventional ANOVA, as for the previous slide, 0.042, and before it was 0.052. So it's expected p-value 0.042 is more significant for fixed cases than for random cases. Now note that whenever covariance 2 minus covariance 3 is less than or equal to 0, that the fixed cases OR as conventional ANOVA and the standard OR will give the same results. Okay, because this correction factor will become 0, and so you get exactly the same results. And we'll see that on another study in a moment. And we can also do a fixed readers version of OR. Again, we tell it affix to readers, and now the p-value is even smaller, 0.019. Okay, again, because we're not generalizing to two populations, but just to one. It makes it easier to get a significant p-value. And the nice thing about this is that output will give you the confidence interval for each single reader. Sometimes you may want that to compare readers. For each reader 1, 2, 3, 4, we get confidence intervals for their AUCs. So even if you're not interested in doing the testing, this is the way to get that out of the software. Okay. I think I lost my chat box, but so you have to let me know if you have a question.
Yeah, well, we don't have any questions at the moment. I think they're saving them all up for the end.
Okay, I'm getting near the end here. Okay. Okay, the readers nested in test study. So this is really the thing I've just been working on recently. Previously, the OR method has been used mostly for studies where each reader reads the same number of cases for each test. That's the factorial design. In contrast, in some studies, readers read the same cases, but for each test, the readers are different. But these are what we call a readers nested in test design. The readers in each test for each test are different. So until recently, OR analysis had been limited to readers nested in test designs where the number of readers is the same for each test. So I showed how to do that back in 2014. But typically the number of readers will differ for each test in a study, such a study. So recently, in this paper I did with Pauline, so she actually sent me the data. I worked on it a few years ago with her, but I didn't have the method to do it with OR. I'll have to tell you about that in a moment. And then when I figured out how to do it in the last year, then I went back to her data set and I presented that in the proceedings this year and writing up a paper of it now. So recently it's been shown how to analyze the diagnostic readers tested and tested with the OR method by the number of readers difference between the tests. Like, see, my typing's getting sloppier near the end. Okay, so here's the study that she got published in 2021. 53 Australian and 15 Singaporean breast radiologists interpreted the same data set as a breast data set with capital BREAST, 60 mammograms of Australian women, 40 non-disease and 20 disease cases. And the purpose was to examine the effect that a test set arriving from one region has on the reader performance from that region and a distant region. We will compare Australia and Singapore AUCs, and then these were based on a 1 to 5 ordinal confidence of disease rating scale. Similar to the factorial study, the OR model for this design is derived by taking into account the correlated errors due to readers reading the same cases by adding a correction term to the conventional model error term, and then adjusting the denominator degrees of freedom accordingly. So there's a conventional model for this design, and then we just take it and we just say, okay, now the errors are going to be correlated. So we take that into account, we create this correction term, and then we create the appropriate degrees of freedom. And that gives us an analysis that generalizes to both the case and reader populations. It's really cool because the MRMC AOV code is exactly the same as for the factorial model. So my programmer is so good, he just has a program figure out that it's the readers nested in test design. And we can also, with the same design, request that readers or cases be fixed, too, using the program. And again, this constraint comes into play again. It's imposed, and it's less than 0, then the results from the analysis that treats both readers and cases as random will be the same as for the fixed cases analysis. So here it is. It looks like the same code as before, really. This different data set. Here's the output. Here are the covariances. Now we see the covariance 2 is less than covariance 3. Okay. And that makes sense that, that these readers are probably kind of similar. So whether they're from the same country or the two of them are from different countries probably doesn't make that much difference. Okay, so because of that, results will be identical to those for the fixed cases model. And then the p-value now is 0.72. So, not a significant difference. But again, more interesting is what's the confidence interval? And this shows, the degree of the differences that are commensurate with the data. So let's see. Australia looks like it's the estimate would be the difference was a little bit, higher for Australia. The estimates are positive. Okay. And then then down here we see the estimates too individually and their confidence intervals. Okay. So these are the kinds of things, to me, this is the interesting part of the analysis, showing what you get here, not just citing the p-value. So it basically shows, the conclusion is, well, they look pretty close, and the confidence interval, shows there could be some difference, but it's not that large. So we could run this for fixed cases, and then we get the same results. Okay, I'm not showing you the output, but as I said, the fixed cases result will be the same as the other one because that covariance 2 minus covariance 3 difference was negative. And we can do it for fixed readers, and for fixed readers now, it drops, the p-value drops to 0.591. Okay, now what about the Wilcox and rank sum test? So I've seen this test used a lot, from your group at the SPI meetings, and it certainly is one you can use. I want to just point out, so it can also be used for comparing two tests for the readers nested in test study. Since then, the reader AUC estimates will be fixed if we treat cases as fixed. I think I wrote that wrong. I meant to say since then the reader AUC estimates will be independent. Sorry about that. So when you fix cases, then there's no correlations, and then the estimates are independent. So you have basically two independent samples of reader AUC estimates. Sorry about that error. Okay. All right, so it's important to make it clear in your write-up, I say, to what populations your conclusions generalize to. Reader population only, case population only, or both populations. So even though the OR analysis for this example for both readers and cases random produce the same results as the one for only readers random, this does not mean that the analysis was not informative. The OR analysis was not informative because for this situation, we can now claim that our results in the OR analysis are applicable to both populations. Okay, whichever one we did. If we only did the conventional, the fixed cases analysis, then we wouldn't be able to claim that. But now that we've done, the main OR analysis, we see that they're the same result. Now, I wanted to say here, okay, so I want to make the point, which I forgot to, about the Wilcoxon. Wilcoxon is a nice test, but oh, here it is. Okay, I think I skipped a slide here. All right. This is oh no, I went through that. Okay, I'm sorry, I'm getting a little mixed up. Okay, the Wilcoxon test, though, it treats cases as fixed, so it has a limited inference. So that is the criticism of the Wilcoxon. You can use it, but you got to remember it only applies to the data set of cases that you've got for the readers. Okay, so that's the advantage again of the OR method. Okay, final slides. The readers nested in test design requires a lot more readers than does factorial design. where readers read under each test. Because in the factorial design, the reader variance drops out due to the within test pairing of reader responses. So for instance, you saw we were using about 15 and 52 readers or something like that in that study, whereas in the other study, we're only using 5 readers total. But again, this nested design does mean you're going to need a lot more readers. Okay. I did not cover sample size issues. I've written a paper and have software for this. So if you're interested, contact me. And by the way, in general, if you have questions, especially, sample size calculation is a very important thing, and it needs to be done correctly in the initial phase of a study. I'm happy to help you, with any questions you have. Just send me an email and I can help you do things like that. The MRMC AOV software is available on the CRAN site. If you are a user, you know what that means. So the OR method capabilities, let me just mention that OR method can be used with any reader performance measure, such as the AUC, empirical and parametric, the partial AUC and FROC measure, sensitivity of fixed specificity, etc. It's a very general method. It can be used with region of interest, or ROI, and location, ROC or LROC studies. It can accommodate partially paired cases. For example, in the SOL study, not all the readers read all of the cases. There were 3 readers. 2 of them read 59 cases, and 1 of them read 58 cases due to a transmission dropout. So we're doing it online, but we can accommodate that. So it's a very powerful method. Now, I should mention about the OR method includes the Gallus method as a special case. The Gallus method is limited to the empirical AUC and mean outcomes, so it's a very specialized method. Specifically, the ORF statistic using the unbiased covariance option is the same as the Gallus statistic, except the Gallus does not impose the constraint on the correction factor to be non-negative. And as a result, the Gallus F statistic can be undefined due to a negative variance, or it can also give a nonsensical p-value that is less than when cases are treated as fixed. So it's nonsensical that you would have more knowledge about both populations than you would have about only one population. So for these reasons, I recommend not using it, at least in its present form. And that is my final slide. Thank you very much for listening. If you have any questions, just let me know.
Thanks so much, Steve. If you'd like to stop sharing your screen, and we'll be able to see everybody
Right.
at once.
Good idea.
There we go. Lovely. We do only have 5 minutes left, so people may elect to contact you via your email, if that's all right, if they have a more detailed question to put to you about your presentation today. Would anybody like to ask Steve a question whilst we have him on the screen? Anyone brave enough to ask Steve a question?
I should warn you, at SPIE, I always ask this question. People give results. I say, no, does that what populations does that result generalize to? And so I'm just warning, if anyone's coming to SPIE this year, that's one of my trick questions.
Right. So we're forewarned to have a response
right for
next February. It doesn't look like we have any questions right at the moment, Steve. I know that we do record these talks, and quite a number of people do catch the recording at a later date, and they may have time, to when they have time, and they may contact you a little after your talk time today.
Yeah. Can I just ask Steve, in studies being submitted now to Radiology and the other journals, are many people using this test, the OR, the ORH test?
Are many people using it?
Yeah, to demonstrate this generalizability.
This is a problem because it seems like fewer and fewer people are using it as time goes on. So, this is an outgrowth of the DBM method, Dorfman-Birbaum-Metz, which was pretty widely used. And I worked with Don Dorfman. That's how I got started, and with Birnbaum too. But I go to these meetings now, and I'm not seeing it. I'm not seeing that many reader studies to begin with. Of course, we have AI studies now. And by the way, we can do AI too, readers with and without AI, and readers versus AI alone. But I'm seeing a real lack of, okay, I'm seeing fewer reader studies, and then I'm seeing when people do reader studies, they're mostly using the Wilcoxon, at least at SPIE. Now, that's not the case for the FDA. I mean, people writing papers to get things approved there have got to use OR, or some people are still using Gallus method. But certainly a SPIE crowd, I mean, I'm not seeing it.
Yeah.
And it's disturbing because there are very few people being trained to even know how to use the method. I haven't tutored anybody, so Nancy Obachowski is kind of off doing other things, and of course Charlie Metz and Don Dorfman died a long time ago, and
Steve.
Sorry. Sorry.
Oh no, I was just going to say, Amir has a question, but Patrick, if you had a continuation of that.
Just a very quick one. Like I remember 10 or 15 years ago, Steve, the Dev Chakraborty's JAFROC approach was commonly talked about at SPI and other meetings, but I don't see so much of that happening now.
It isn't either. Now Chakraborty, of course, basically uses OR, but he uses it with the FROC performance measure. Yeah, I mean, according to what he says in his book, I don't know if have you seen his book?
I have seen it, yeah.
Yeah, I mean, he says, that it's used more in Europe than in the US. I mean, some of us in the US, I mean, I've always felt, I mean, it's a valid measure to use, but it's kind of hard to interpret it, especially in terms of when you have a confidence interval. I mean, if you weren't doing more than just getting a p-value for reject or accept a hypothesis, things are different. It doesn't have that nice interpretation that the AUC does. My own sense is I would prefer to use something more like an LROC approach, where you can see if a person will score the reader will score a person for disease, and then also see if they can locate the lesion correctly. And if they do both, then they get credit. Okay. And it's easy to do that. It's a little different kind of analysis. But yeah, he's you're right. I'm not seeing that hardly at all.
Thank you, Steve.
It's not encouraging, I have to say, that we seem to statistically being sort of backsliding in this field. That's my impression.
Thank you. Amir, I think we're out of time and people are probably heading off now, but did you have a question?
I have, but if you need to conclude the meeting, I can email Steve. It's up to you. And
I'm happy to hang on here.
okay, so it will be quick. I just wanted to ask if the OR method is sensitive to variations in the number of lesions in two modalities. If we are comparing modality X with modality Y, and the number of lesions on the cases are different, that is something we are facing in our current phase contrast imaging project, comparing CT images with mammography. But sometimes the lesions are visible on mammography and not on CT. Mainly because of the time gap between taking the images, and neoadjuvant therapies or biopsies happen between taking those images. So can we still use OR methods?
Are you using you want to do a lesion, analysis that treats lesion as the outcome, as opposed to the case?
So we are measuring sensitivity, lesion sensitivity, and JAFRAC, all of them.
JAFRAC.
Yeah.
And so I guess I'm not sure exactly what your question is again then.
So it's mainly having the same cases from the same patients, but because of the time gap between taking the images in the two modalities, the lesions are not equivalent. So when we are marking the truth on the images, we are not seeing the same lesions in modality Y and modality X.
I mean, because there was a time period, so the patient is called back again at some later time for the second modality. Is that what you're talking about? And then, okay.
Yeah.
Well, the way you could get around that is, I guess you could randomize the patients. I mean, if you could randomize the order of which modality was taken first on the patient, the images were. But you're right.
But the image types are quite different. So one is 2D images, the other one is 3D images. So when you say randomize, you mean?
You can't.
The
sequence of patients would always be the same. Modality one will have those patients first, that group of images first, and modality two would have. You can't sort of randomize that because something
I don't know. I don't quite understand exactly all the details enough to answer quickly, but it's a good question. I mean, we could talk some more about it. I'd be happy to. I mean, the thing is, we have flexibility too to come up with new ways, new kinds of performance measures. I mean, now you're talking about the JAFRAC method. The one thing I don't like about that method is, that there's no penalty for making marks on a disease lesion on a disease case where there's no lesion. There's no penalty for that. And I think that's a shortcoming of it. That the best way to score good on a JAFRAC, study is that if you think it's diseased, then you take confident you think the image is diseased, and you mark all over the image. You see, because there's no penalty if you're marking here. If you think, I think it's likely to be diseased with a 4, then I'll just mark all over it so I don't miss the lesion. Because there's no penalty for all those marks where there's no lesion. So that is, I think, a criticism of that statistic. But what we can do is we can, people like me and you can sit down and think, what would make a reasonable type of performance outcome, and then we can analyze it once we get that. And the OR method will work with any performance measure that we come up with. We're not just limited to what people have thought of before. And I think the other criticism of the JAFRAC thing is, that was good when you had 2-dimensional images, but it gets a little more difficult in 3 dimensions, I think.
Yeah, very interesting. Yeah.
Thank you, Sue.
Okay, we might wrap it up there. Thanks, Steve. We let you go enjoy your evening or some dinner.
Okay.
And it was a great pleasure to have you and see you looking so well on the screen again today. Thank you very much for your informative talk. And I'm sure there's quite a number of questions coming your way via Curly emails.
And I really actually encourage you to send me questions. And also, I am actually, but I'm in the process now. My grant is over with, and I'm working at 1% on Claudia's grant. It makes me above zero, but actually, I'm retired in a sense. I have enough income coming in that I don't actually need to make a living, and I'm actually working on finishing up papers from the last grant and writing a book. And I'm looking for data examples for the book and for my papers too. And I, if people want to get credit and get on papers and have their data sets known, you're a good source of data sets there in Sydney. So, and I don't really have anybody here at the University of Iowa to work with on reader studies because they're not hardly done. So here, so I appreciate any kind of collaboration that you might be interested in.
Yeah, there's lots coming your way.
We tend to have lots of data, Steve. So let's talk more in Chicago. I'm sure we can
Okay,
find
that sounds good. I appreciate it, Patrick.
that out.
Thank you very much. Okay.
See you later. Good evening,
Okay.
Steve. Good morning,
Thank
everyone.
you, everyone.
Thank you, Steve.
Bye.
Bye.